Right now, as you watch this video, you're aging. Every second that passes is gone forever. You can't rewind it. You can't pause it. And here's the truly disturbing part. Physics can't actually explain why. In fact, almost every law of physics says time should work just as well backwards as it does forwards. So why doesn't it? Why can't you unbreak a glass, unburn a piece of paper, or watch smoke flow back into a candle? The answer is way more unsettling than you might think, and it suggests something genuinely terrifying about the fate of everything in the universe, including you. I'm going to show you why time only moves in one direction. And trust me, once you understand this, you'll never look at a melting ice cube the same way again. But before we dive into one of physics' deepest mysteries, hit that subscribe button and turn on notifications. Because here at Physics Decoded, we're breaking down the universe's most mind-bending secrets in ways that'll actually make sense. Let me ask you something. When was the last time you saw a broken egg spontaneously reassemble itself? When did you last see cream separate itself from coffee and float back to the top? Never, right? These things just don't happen. But here's what'll blow your mind. The fundamental laws of physics, the actual equations that govern reality, they don't forbid any of this. Newton's laws work perfectly fine in reverse. Einstein's relativity doesn't care which direction time flows. Even quantum mechanics is mostly reversible. So what's stopping that egg from unbreaking? This is called the arrow of time problem, and it's been haunting physicists for over a century. Time seems to have a direction, an arrow that points from past to future. We remember yesterday but not tomorrow. We see things break but never spontaneously repair. The universe seems to be running in one direction only, like a movie that can only play forward. But why? What makes the future different from the past? The answer lies in something you've probably heard of, but never really understood: entropy. And I'm not going to give you the boring textbook definition. Instead, picture your bedroom. If you're like most people, it doesn't stay clean on its own, does it? It naturally tends toward mess. Clothes pile up, books scatter, dust accumulates. That's entropy in action. It's the universe's tendency to go from order to disorder, from organized to chaotic, from structured to random. But entropy is so much more than just messy rooms. It's the reason you age. It's the reason stars burn out. It's the reason you can't untoast bread. And here's the really wild part. Entropy is the only thing in all of physics that gives time a direction. It's not just that things tend to get messier. It's that this tendency literally defines what we call the future. The future is simply the direction in which entropy increases. Think about an ice cube melting in a glass of water. The ice is organized, all those water molecules locked in a neat crystalline structure. As it melts, that organization breaks down. The molecules spread out, mix with the water, become disordered. Entropy increases. Now, nothing in the laws of physics says this can't happen in reverse. The equations would work just fine if all those water molecules spontaneously organized themselves back into ice. But they don't, and they won't. Not in your lifetime. Not in a trillion lifetimes. The reason gets into probability, and this is where things get really interesting. Imagine you have a box divided in half by a removable partition. On one side, you've got 100 gas molecules. On the other side, nothing, just empty space. Now you remove the partition. What happens? The gas spreads out to fill the whole box, obviously. The molecules bounce around randomly until they're evenly distributed throughout the entire space. That's an increase in entropy. Now, here's the question. Could those molecules, just by random motion, all end up back on one side of the box? Technically, yes. The laws of physics allow it. Each molecule is just bouncing around randomly, and there's nothing stopping them from all randomly bouncing back to where they started. But the odds of this actually happening are so astronomically small that it might as well be impossible. We're talking about odds like 1 in 10 to the power of 30. That's a 1 with 30 zeros after it. You could wait longer than the current age of the universe and you still would unsee it happen. This is the key insight. Low entropy states, organized states, are rare. High entropy states, disordered states, are common. There are countless ways for those gas molecules to be spread throughout the box, but only one way for them all to be on one side. So, just by random chance, the system will naturally evolve toward the more probable state, the higher entropy state, and that evolution defines the arrow of time. But wait, you might be thinking, if the laws of physics work the same forwards and backwards, shouldn't we see time running backwards just as often as forwards? Shouldn't there be some parts of the universe where eggs unbreak and smoke flows back into candles? This is where we hit the really disturbing part. The answer seems to be no, and the reason why reveals something deeply strange about the universe. See, for entropy to increase, for time to have the arrow we observe, the universe must have started in an incredibly low entropy state. The Big Bang wasn't just the beginning of space and time, it was the beginning of order. The early universe was extraordinarily smooth, extraordinarily uniform, extraordinarily organized, and ever since that moment, entropy has been increasing. The universe has been getting messier, more disordered, more chaotic. The Big Bang could have started in a high entropy state. It could have been completely random and chaotic from the very beginning, but it wasn't. It was incredibly ordered, and nobody knows why. Some physicists call this the past hypothesis. It's the assumption that the universe began in a very special, very low entropy state. Without this assumption, we can't explain the arrow of time. We can't explain why eggs break but don't unbreak. We can't explain why you remember the past but not the future. The entire direction of time depends on this mysterious initial condition that we don't understand. And it gets weirder. If you do the math, if you actually calculate the odds of the universe starting in such a low entropy state, just by chance, the numbers are incomprehensibly small. We're talking about probabilities that make winning the lottery 1,000,000 times in a row look like a sure bet. It's so unlikely that it seems like it can't be an accident. The universe appears to have been carefully prepared, set up in just the right way to give time its arrow. Now, let me show you just how bizarre this really is. Imagine you walk into a room and you see a wine glass sitting on the edge of a table. You bump the table, the glass falls and shatters on the floor. You'd think nothing of it, right? Gravity pulled it down, it hit the ground, it broke. Entropy increased. Makes perfect sense. But now, imagine this. You walk into a room and you see broken glass on the floor. As you watch, the pieces spontaneously leap up off the ground, assemble themselves into a perfect wine glass, and land gently on the table. You'd think you were losing your mind. But here's the thing. From a physics standpoint, both scenarios are equally valid. The equations don't prefer one over the other. The only difference is entropy. The breaking glass increases entropy. The unbreaking glass decreases it. And we only see the first one because the universe happened to start in a low entropy state. If it had started in a high entropy state, you'd be just as likely to see glasses unbreak as break. Time wouldn't have a preferred direction at all. Think about what this means for your life. Every memory you have, every experience, every moment, exists only because the universe started in this special state. Your very consciousness, your sense of time flowing from past to future, is a consequence of entropy. You don't remember tomorrow for the same reason eggs don't unbreak, because entropy is increasing, and that increase defines what we call the future. Let me give you another example that really drives this home. Think about a video recording. You can tell if a video is playing forwards or backwards, right? If you see a diver jump off it, when you watch a video of a diver, they leap from the board, enter the water cleanly. Then the video reverses, and they fly back out. You know something's wrong. But why? What is it about the reversed video that looks wrong? It's entropy. The forward video shows entropy increasing. The diver goes from an organized state on the board to a less organized state in the water, splashing, creating ripples, disturbing the system. The reversed video shows entropy decreasing, which violates our deep intuition about how time works. But some processes look the same forwards and backwards. If you watch a planet orbiting a star and you reverse the video, it still looks perfectly normal. The orbit works just as well in either direction. That's because these are reversible processes. They don't significantly change the entropy of the system. Time's arrow is hidden in them. It's only in irreversible processes, processes that increase entropy, that we can clearly see time's direction. And this brings us to one of the most unsettling implications of all this. If entropy always increases, if the universe is always getting more disordered, what's the end result? Where is this all heading? The answer is called heat death, and it's exactly as grim as it sounds. Eventually, in the unimaginably distant future, the universe will reach a state of maximum entropy. Everything will be spread out uniformly. There will be no differences in temperature, no concentration of energy, no structure, no stars, no planets, no life. Just a thin, cold, dark soup of particles spread across an expanding void. Nothing will happen anymore because there will be no entropy left to increase. Time, in a sense, will stop. This is the ultimate fate predicted by the second law of thermodynamics, the law that says entropy always increases in a closed system, and the universe is the ultimate closed system. There's nothing outside it, no way to decrease its overall entropy. So it's marching, slowly but inevitably, toward this state of maximum disorder. Every star that burns is bringing us closer. Every chemical reaction, every movement, every thought in your brain is contributing to the universe's long, slow slide into heat death. Now, I know what some of you are thinking. What about black holes? Don't they decrease entropy by sucking everything in and organizing it into a single point? This is actually one of the most fascinating discoveries in modern physics. In the 1970s, physicist Stephen Hawking proved that black holes actually have entropy, and not just a little bit. A black hole has more entropy than anything else of the same size in the universe. When matter falls into a black hole, the total entropy of the universe still increases. Black holes don't violate the second law. They're actually entropy monsters, the ultimate disordered states, and there's more. Hawking also showed that black holes emit radiation, now called Hawking radiation, and they slowly evaporate over time. A black hole isn't forever. Given enough time, trillions upon trillions of years, even black holes will decay, and when they do, they'll contribute to that final heat death, that maximum entropy state where nothing interesting can happen anymore. But let's bring this back to something more immediate, more personal. You're made of about 37 trillion cells. Each one is an incredibly complex, highly organized structure. Proteins folded just right, DNA storing information, membranes keeping the inside separate from the outside. You are a low-entropy system, and every second of your life, you're fighting against entropy. You eat food to bring in organized energy. You breathe oxygen to power the chemical reactions that keep you going. You're constantly working to maintain your structure, to keep yourself organized, to prevent the disorder from taking over. But you can't fight forever. Eventually, entropy wins. Your cells break down, your structures degrade, your organization dissolves. That's aging, that's death. It's not a malfunction. It's not a disease that might someday be cured. It's a fundamental consequence of the second law of thermodynamics. You exist as a temporary pocket of low entropy in a universe that's relentlessly increasing toward disorder. And yet, here's something beautiful in all this darkness. The fact that you exist at all, the fact that stars shine and planets form and life emerges, is remarkable precisely because it's fighting against the tide of entropy. Every living thing is a local decrease in entropy, a temporary victory of order over chaos. We're powered by the sun, which is burning through its fuel, increasing the entropy of the solar system. But in doing so, it gives us the energy to create structure, complexity, thought, consciousness. Life is the universe's way of creating interesting things before the heat death. We're not separate from this cosmic story. We're part of it. Every thought you think, every action you take, is a brief, beautiful, improbable eddy of order in the great river of increasing entropy. And that makes every moment precious, because it's one of the few moments the universe gets to experience low entropy, to experience structure, to experience meaning before it all dissolves. Now let us talk about something that might sound like science fiction, but is actually a serious area of research. What if the arrow of time isn't the same everywhere? What if there are parts of the universe where time runs differently, or even backwards? Some cosmologists have explored models where the Big Bang wasn't the beginning of everything, but rather a low-entropy point in a much larger multiverse. In these models, there could be regions where time flows in the opposite direction relative to us. If you could somehow visit such a region, from your perspective, you'd see cause and effect reversed. Effects would come before causes. People would grow younger instead of older. It sounds absurd, but it's mathematically possible. There's also the question of what happens inside black holes. We know that the normal rules break down at the singularity. Space and time swap roles. Some physicists speculate that time itself might behave strangely beyond the event horizon. Could there be regions inside a black hole where the arrow of time reverses? We don't know. We can't observe it. But the equations leave room for these possibilities. And then there's quantum mechanics, which throws another wrench into our understanding of time. At the quantum level, processes can be reversible. Particles don't have definite states until they're measured. The past isn't fixed in the same way it is in our everyday experience. Some interpretations of quantum mechanics suggest that the arrow of time emerges only when quantum systems interact with the larger, classical world. The measurement process itself might be what gives time its direction at the microscopic level. But even with all these exotic possibilities, the fundamental mystery remains. Why did the universe start with low entropy? Why is there an arrow of time at all? Some physicists think the answer might lie in quantum gravity, a theory we don't yet have that would unite quantum mechanics and general relativity. Maybe at the moment of the Big Bang, quantum effects created the conditions for low entropy. Maybe the arrow of time is built into the fabric of spacetime itself in ways we don't yet understand. Others think we're asking the wrong question. Maybe the universe didn't start in a low entropy state by chance or by design. Maybe there are selection effects at play. Maybe only universes with low entropy initial conditions can support observers like us who can ask these questions in the first place. This is a version of the anthropic principle, and while it's controversial, it points to a deep connection between the arrow of time and the existence of life and consciousness. Here's another mind-bending thought. What if your entire life, every memory you have, every experience, was just a random fluctuation in a high-entropy universe? Imagine the universe has been in heat death for an eternity. In such a state, random quantum fluctuations could, given infinite time, spontaneously create anything. They could create a brain, complete with false memories of a whole lifetime, that exists for just a moment before dissolving back into chaos. This is called a Boltzmann brain, and if the universe is eternal, there should be infinitely more Boltzmann brains than real observers like you. The fact that you seem to be a real person in a real ordered universe is another piece of evidence that something special happened at the beginning. Let me bring this all together. Time moves forward because entropy increases. Entropy increases because the universe started in a low entropy state. We don't know why it started that way, and that's one of the deepest unsolved problems in physics. The arrow of time isn't written into the fundamental laws. It's a consequence of initial conditions, of the particular way our universe happened to begin. And that beginning determines everything, from the fact that you can't unbreak an egg, to the fact that you're re-aging right now as you watch this video, to the ultimate heat death of the cosmos. So what does this mean for you? It means that every moment is part of a one-way journey. The past is gone, locked away, inaccessible except through imperfect memories. The future is open, unwritten, full of possibilities, but constrained by the relentless increase of entropy. You can't go back. You can't undo. You can only move forward, surfing the wave of increasing disorder, creating temporary pockets of meaning and structure before they too dissolve. But there's also something profoundly liberating about understanding this. You're not fighting against the universe. You're part of its natural flow. Every choice you make, every action you take, is adding to the story of how order briefly emerged from chaos before returning to it. You're writing your chapter in the great cosmic narrative of entropy. And maybe, just maybe, understanding the arrow of time helps us appreciate the time we have. We can't slow it down, we can't reverse it, but we can choose what we do with it. We can choose to create, to build, to love, to think, to learn, to share. We can choose to be one of those beautiful, improbable pockets of low entropy that make the universe's journey toward heat death a little more interesting. So here's what I want you to do. Drop a comment below and tell me, does understanding the arrow of time change how you think about your own life? Does it make you want to use your time differently? I read every comment, and I love hearing your perspectives on this stuff. And if this video bent your mind even a little bit, share it with someone who needs their universe rocked. Send it to that friend who's always asking deep questions. Post it on your social media. Let's get more people thinking about the profound weirdness of time. The arrow of time is still pointing forward. Entropy is still increasing. And you're still aging, but now you know why. Now you understand the terrifying, beautiful, inexplicable fact that the universe started in a special state and has been running downhill ever since. And that makes you, your life, your thoughts, your experiences, all the more remarkable. You're a temporary reversal of the cosmic tide, a brief moment of order in an ocean of chaos. Make it count. Thanks for watching Physics Decoded. If you want more deep dives into the mysteries of the universe, hit subscribe and turn on notifications. I've got videos on black holes, quantum mechanics, the nature of reality, and so much more. The universe is strange, and we're just getting started on figuring out how strange. I'll see you in the next one, where we'll keep decoding the cosmos, one mind-blowing concept at a time.